Okay, so in this last part, looking at section 7D, I wanted to kind of like maybe make things a little bit more concrete, if that's the right word, about what the polar decomposition theorem is actually telling us in terms of matrices. And one way to express what the polar decomposition theorem is telling us is that given an n by n matrix, you can find an orthogonal matrix U and a positive semi-definite matrix R. So just remember what this means. R has non-negative eigenvalues such that two things are true. First of all, that R squared is equal to A transpose A, and A is equal to U times R. Okay, so if you want to think about it in terms of the operators, right, the U here is the matrix analog. This is the matrix analog of isometry, because orthogonal matrices correspond to isometries, and this guy over here is the matrix analog of the square root of, well, I guess I should say the square root, okay, of the operator, because of this property right here. Okay, so that's really kind of the matrix version of what we've been doing. Okay, and it's actually not so hard to find this decomposition, right? Under one extra hypothesis. So if your matrix A is invertible, it's actually easy to find this decomposition. I mean, you may quibble with the word easy here, but it's kind of straightforward to explain. You don't really need anything more than math 1B03, because what you do is, first of all, you compute A transpose A, and you find the diagonalization of this matrix, A transpose A, which is equal to PD P inverse. Okay, and that's, you can always find a diagonalization because this is going to be a symmetric matrix. And I'm assuming here that everything is over R. Okay, so over the real numbers. Then we let our matrix R that we need for the theorem to be simply the matrix P, and then what you're doing is you take the square root of every entry on the diagonal matrix D, where D is equal to D1 through Dn. Okay, and finally, since A is invertible, we know that the matrix U that we're looking for has to satisfy A times R inverse. Okay, so in the end of the day, we're actually find the R, and we're given the A, so we can find the U that we're looking for. So let me just walk through this procedure with a concrete example. Let's say we want to find the polar decomposition of this matrix. The first step is I compute A transpose A. So I do that, and I actually use Octave to do a lot of these calculations, so I know it looks like I'm going a little quick, but I get this matrix right here, and as expected, I get a symmetric matrix. Now I can diagonalize this matrix, and when I diagonalize it, I get this matrix. Times the inverse of the first matrix, right? 1, 2, minus 2, 1. So that's the inverse. And so that's the first step. Now I create my matrix R. My matrix R is, this is my P, this is my D, and this is my P inverse. So I keep the P and the P inverse. So I have 1, 2, minus 2, 1. But for this one, I take the square root of all the values, right? And then over here, I have 1, 2, minus 2, 1. And I actually went and computed this. So this is 2.8, 0.4, 0.4, and 2.2. And again, I want to point out that you're getting a matrix R, right? It should be a positive operator, so that one of the things it should be is it should be symmetric. And then finally, um, I think I made a mistake here. Since A is invertible, I think I rearranged my equation a little. No, this is right. Since A is invertible, we have to use some properties about invertibility, about moving things around. We have that this matrix here, U is equal to our original matrix A, which was 2, 2, minus 1, 2. Oh, sorry, that's the transpose. Times this matrix right here, 2.8, 0.4, 0.4, 2.2, and this gives me 0.8, 0.6, negative 0.6, and 0.8. Okay, and so at the end of the day, we have the following decomposition. We have 0.8, 0.6, negative 0.6, and 0.8 times the matrix 2.8, 0.4, 0.4, and 2.2. And so this matrix here is orthogonal, right? Because the columns are definitely orthogonal, and the length of each vector, I should have double checked this, but the length of each vector should be 1. And over here, this is a symmetric matrix, and whose square is equal to this matrix right up here. So this is the decomposition that we're looking for. Okay, so this is a kind of a pretty deep result. There's only one main idea here is polar decomposition, and we're going to be using that in our last lecture. Okay, so I'll stop here and I'll see you in the next lecture.